All right, let's dive right into this explainer. We're going to trace humanity's decades-long quest to teach computers how to stop just reading words and start actually understanding their meaning. Think about it. We interact with search engines and databases every single day, right? But have you ever stopped to wonder how these systems actually know what you're looking for? Because for a really long time, they didn't. They just faked it, and they faked it really well. To really grasp how this works, we have to introduce the ultimate villain in the history of information retrieval. We call it the semantic gap. This was basically the inherent flaw in early computer systems. Sure, they could rapidly match words on a page, but they had absolutely no idea what those words actually meant. They could find the letters for the word bank, but they couldn't tell if you meant a financial institution or the side of a muddy river. And honestly, this gap, this huge disconnect between human meaning and machine processing, has driven a massive, truly fascinating evolution in how we index knowledge. So let's move into Section 1, the search for meaning. Which brings us right into Section 2, the traditional indexing era. You see, as the sheer volume of human information exploded over the last century, especially with all the scientific literature coming out, the old goal of simple findability just wasn't enough anymore. Pointing to a document on a massive library shelf wasn't going to cut it. Now, in what we call the syntactic era, early automated systems were the absolute heroes. They were incredibly fast, but they were rigidly organized around documents. Pioneers tried to fix this. In the late 1950s, you had systems like KWIC, grabbing keywords directly from titles. Super fast, sure, but incredibly shallow. Then there was chain indexing, which relied entirely on class numbers, meaning it completely broke down if the underlying classification scheme was flawed. Later on, systems like Precis and POPZ tried to map out context using complex syntax rules and elementary categories. And hey, they definitely sped up document retrieval. But they consistently failed to explicitly map out the actual semantic relationships between those ideas. So overcoming this required a massive paradigm shift. We were stuck in syntactic indexing, literally organizing documents by matching rigid keywords and codes. But to close that semantic gap we just talked about, we desperately needed semantic indexing. This means organizing real-world knowledge by truly understanding context and relationships. It's kind of like the difference between just pointing at a picture of a dog versus actively understanding that a dog is an animal, it's a pet, and it barks. Making that leap from syntactic to semantic, that changes absolutely everything. Let's explore Section 3, the Semantic Web paradigm. Enter the visionaries who realized we had to move way beyond organizing static documents. They saw that to make computers truly helpful, we had to start formally mapping out domain knowledge. This gave rise to ontologies, which are structured frameworks built with descriptive logic to rigorously represent the types, properties, and really intricate interrelationships of concepts. The main pioneer of this huge vision was Tim Berners-Lee. He imagined transforming the entire web from a chaotic pile of unstructured documents into a cohesive web of data explicitly designed to be processed by machines. Just imagine a world where previously isolated pieces of information are suddenly connected through linked data using unique uniform resource identifiers. It was a massive technological revolution. The whole goal was teaching machines to literally understand the underlying structure of our world. But to make the semantic web actually work, we needed a completely new language. So the Resource Description Framework, or RDF, steps in and breaks information down into machine-processable triples. It's actually pretty elegant. You have a subject, let's say the sky, a predicate expressing the relationship, like has the color, and an object, blue. This simple three-part structure suddenly gave computers the ability to read actual facts instead of just dumb strings of letters. And researchers just kept refining this approach. Frameworks like DRA, that stands for Domain, Entity, Relation, and Attribute, pushed it even further. Instead of just linking abstract concepts, DRA explicitly focuses on physical, real-world named entities. So, for example, instead of just tracking a generic document about Italy, it defines a specific Italian mountain, say Monte Bondone, and it tracks its exact altitude, its geocoordinates, and the explicit semantic relationships it has with the world around it. Now for Section 4, Rise of Knowledge Graphs. While the semantic web laid all that great theoretical groundwork, it was the introduction of knowledge graphs, which Google really took mainstream around 2012, that made these semantic principles immensely practical and scalable on a global level. But what actually is a knowledge graph? Well, it's a structured representation of diversified knowledge, where nodes are real-world entities and edges are the logical connections between them. Think of it like a giant, interconnected detective board. Instead of a file folder stuffed with disconnected documents, you've got pins on a board representing people, places, and concepts, with that red string explicitly connecting how they all relate to one another. It completely shifted the focus from finding documents to retrieving actual knowledge. And we didn't just stop at basic graphs either. We started out with static knowledge graphs, which were essentially rigid, fixed dictionaries. But real-world knowledge changes, right? So we quickly evolved to dynamic knowledge graphs that constantly update. Then came temporal knowledge graphs, adding the dimension of time, which allows systems to track how facts change throughout history. And today we're pushing into event knowledge graphs, tracking complex, multi-layered events exactly as they unfold in real time. Now you're probably wondering, how on earth do we process all this at scale? The answer, of course, is artificial intelligence. AI has absolutely supercharged this whole revolution. Natural language processing allows systems to grasp human context. Machine learning algorithms actually learn from what you intend to search for. And deep learning neurons works. They can process massive mountains of unstructured data, things like images and social media posts, to intuitively predict missing facts and automate the extraction of knowledge. AI is literally the roaring engine making these massive graphs function. Which leads us to Section 5, the complexity trade-off. Because creating a perfectly machine-readable world isn't exactly a walk in the park. In fact, it comes with a massive cost. Here's the core dilemma we face. On one hand, you have the theoretical power of semantic indexing, unparalleled precision, comprehensive recall, and this incredibly rich, interconnected context. But on the other hand, you have its major villain, practical friction. Building these ontologies requires extreme complexity and a dramatically steep learning curve. Researchers actually compare the difficulty to creating a full MARC catalog record. The incredibly strict ancient data rules physical libraries use to meticulously track books. It takes immense specialized knowledge, human effort, and resources to build these structures without making errors. To put that into perspective, consider the year 2014. That was when the W3C published key linked data vocabulary recommendations to try and get everybody on the same page. Yet even today, years later, the limited availability of these standardized vocabularies still bottlenecks the semantic web. We have the technology, sure, but standardizing human knowledge so everyone universally agrees on it, that is practically and socially incredibly difficult. Finally, let's look at Section 6. The future of knowledge. We are entering an era of unprecedented human-AI collaboration in information retrieval. The crucial takeaway here is this: the future is all about bridging the gap between theoretical semantic richness and practical usability. And how do we do that? Well, by integrating large language models to automate knowledge extraction, so humans don't have to manually code every single relationship. We do it by utilizing collaborative platforms and user-generated tagging to build knowledge collectively, and by developing smarter AI frameworks to handle the messy, inherent ambiguity of human language. Essentially, AI is going to do the heavy lifting of building the semantic web for us. Which leaves us with a pretty profound question to wrap up this explainer. We've spent decades trying to close the semantic gap, meticulously teaching machines what our words actually mean. But if indexing is no longer just about finding a document, and instead is about actively mapping out all interconnected human knowledge, what happens when the machines sitting on top of these massive graphs begin to understand the relationships and patterns of our world better than we do? It's a fascinating, maybe slightly wild future to look forward to. Thanks so much for exploring it with me.